We're going to look at a tool now that's useful for representing the one-step transition probability matrices that we talked about before. These are graphs. More specifically, they're directed graphs. And we'll try these out on a couple of different examples. One that we've seen already, so that the example itself won't really be a surprise, but the other one will be a new example for us. So the idea of a graph is that there are nodes and there are edges. And a directed graph is such that there's a direction that goes along with those edges. So we're going to so the nodes on our graph are going to be states. States of the system that we're trying to model. So we'll make that clear in a second from our example. And the edges are going to be the transition probabilities. But again, they're directed. So these are directed edges. And these are our transition probabilities. The probabilities for transitioning from one state to another or one node to another in one step. Right? So the first thing I want to try, the first example I want to try it on is the gambler's ruin. So this is an example of how to use a directed graph for a Markov chain. So we're going to use the gambler's ruin problem again. And if you remember, this one was set up in the following way. We had the chain is made up of x sub n, and this is equal to the number of tokens, the number, or I think I wrote it like, I think I just called it player A's tokens. After game n. So in this case, this can be equal to 0 if the player A has just lost the game, or 1 and 2 and so on, up to whatever they started with initially, which was A. But it can be more than that, right? They can win money from player B or tokens from player B. So it can get to, at most, A plus B, right? And if that happens, then player A has won the game. So again, I'll just remind you, A is equal to x0. So that's player A's tokens at the start of the game, or before the first game, after game 0. And B is equal to player B's initial tokens. Right? And and remember the way that this game is played is that you have probability P that player A wins. An individual game. And these are each game, there's a game played at every step. And then Q, which is 1 minus P, that's the probability of a fail, or that B wins. That A loses a game. Okay. Now, before we start trying to explore the graph, remember it's kind of important if we're going to use one-step transition probability matrices, since the indices of, or since the elements of that matrix are the transitions between the states, it's easiest for us if we have a convention for what do we call the element in the top left corner of the matrix, right? So you have a matrix here like this, and there's elements all around, and so on. What do you call the location of this guy? Do you call that 0, 0, or -2, -2, or 1, 1? And so we're going to go with the convention that that location is 1, 1. And as a result, we have to rename all the states, which are the indices of that matrix, in such a way that they start at 1. All right, so we're going to name the states, or the state space. All right, so that's S. Right, and we're going to name them, or just sort of remap them, so that these are equal to the set of all possible values of A's capital, number of A's tokens, plus 1. This way, the lowest value that a state can have is, or the smallest label that a state can have is 1, when A has no capital, when they've lost the game. All right, so let's try to draw what this graph should look like. So over here, we're going to put on the left side of the picture, so we'll go over here, so we'll put on the left side a box. That's a node, and we'll label it number 1. And so that's state number 1, right? So that's where we are when A has lost the game, all right? And then next to that, we're going to have state number 2. That's where we are when A has 1 token, and so on. So we'll put 3 over here. And then all the way up to how high can we get? How many tokens can A have at most? It can have A plus B tokens, but this state label is not the label for the number of tokens, right? It's the number of tokens plus 1. So let's do this. So let's say this is A plus B. And then one box over will be, I better write the thing first, A plus B plus 1, right? So now these two boxes on the ends, 1 and A plus B plus 1, those are the ending points of the game. At those points, the game can't progress any further because A has either got all the money or none of it, right? So for any of the intermediate points, so let's say 2, the node at node number 2 here, labeled number 2 here, this guy has a probability of going up to node number 3 if A wins a game. And so we draw this like this. You can draw straight lines. I like to draw them as little curved lines. And then we write on top of it the probability of having that transition. And that's the transition. That transition means that A has won a game. And so the probability for that is P. Right? And if you were in state number 3, A could lose a game and get put back into state number 2. And so we draw that like this, and we label that Q, right? And so these arrows continue, one going forward and one going backward, all along here. So there's one that comes into here with probability P, and there's one that goes away from here with probability Q. And there's also one that goes here with probability Q. And there's one that goes here with probability P. Right? Now, there's 2 other lines that we should, or edges that we should draw on this graph, directed edges. And these are what happens when you're at the endpoints. So if A wins a game at the end, well, what does that even mean? So in other words, you're in state endpoint. What's the probability of you leaving? And it's 0. So the probability you draw, when that's the case, when you're stuck and you can't get out of the state, you draw an arrow returning to the state, and you put a probability of 1, right? It could be that there's some situations where you have an arrow coming back to the same state, and it's not you're not stuck in that state, but it's just one of the possibilities. And then similarly, for state number 1, you can't escape from there, because that's where A has lost the game, and that has a probability of 1 pointing back at itself, right? And so that's our directed graph for the gambler's ruin, right? And so let's make a note to ourselves: game ends at states 1 and A plus B plus 1. Okay, that's the little gambler's ruin problem represented as a directed graph. Now let's try a new one that we haven't seen before. So this one is going to be, I'm just going to name it coins. So this is another example, but we've not actually seen this example before. So we'll call this guy coins. And this is, you just flip one coin over and over again. All right, and so that's the name of this game. And in fact, it's what we're going to try to do is 4 heads in a row. And in a row it means like sequentially. So the goal of this game is to have 4 consecutive coin tosses that result in heads. And then the game is finished, right? So that's the game. And let's suppose that you have the probability of heads is P. Of 1 heads, that's P. And probability of tails or of not heads so that's 1 minus P or Q. Right, so similar to the previous game, there's either like a success or a fail. But in this case, the success is you got another head in a row. And so that has probability P. But you want to keep going until you have 4 heads in a row. So that's the idea. And so the chain now is going to look like this. So we're going to call it X sub T, where T is time. Maybe we should have used T before. But what this is, this quantity, it's the current number of heads in a row or the current number of sequential tosses of heads. But again, we want to make it so that the states are labeled starting at 1. So the smallest state label will be 1. And so we're actually just going to rename the chain, the random variables that make up the chain here. So we'll say it's this quantity, current number of heads in a row, plus 1, right? So we've renamed the x's here, right? And therefore then our states look like this, same as before, almost, right? So it's state space is 1. So when you have 1, that means you have no heads in a row. So that could be like the very first toss. You've not had anything. Or it could be way late in the game after 47 tosses when you were close to getting 4 in a row. And then you flip the tails, and then now you're starting again with no heads in a row. And so you can have 2, and so on. What's the highest number this can be? Number of heads in a row, the game stops when you get to 4. And so therefore the largest label you can have for the state is 5. Current heads in a row plus 1. And that's the whole state space here. So unlike the Gambler's Ruin one, there's this sort of like infinite series or potentially infinite series, so we can't actually see the whole graph here. But in this case, we can, because there's only 5 individual states, and so we can completely represent it without anything like that. And so let's start this off. So again, you're going to win, or the game is finished at either this place or these 2 states is where the game is ending. So we expect those 2 to have little arrows coming back to them with 1. But there's a little bit of a different situation here. So I'm going to put number 1 over here on the side. But number 2, I'm going to put below it. So this is sort of part of the fun of these graphs. You don't have to put things in this arrangement the way I'm doing. But you can try different arrangements and see if it makes, sometimes it gives you a more clear understanding of what's happening, and you can try these different things. So state 3 is over here, and then I'm going to put 4 over here, and 5 over here. All right, let's give it a little more room there. And now let's think about all the different probabilities. So first of all, if you're in state 1, well, let's go back over here. I think I said something that's incorrect here. Maybe you've already noticed it. But if you're in state 5, the game is over, right? That means you've had 4 heads in a row. And so there you've got a 1, right? But what about if you're in state 1? I think I suggested that there should be a probability coming back to that, which is true. But what is the probability of returning to state 1 if you're in state 1? Well, if you're in state 1, that means you've had no heads in a row. So you're definitely going to throw the coin again. And the probability of coming back to state 1 would be if you threw a tails, right? You still had no heads in a row. And so there's an arrow coming back around like this. And the probability on that is Q, right? Now, alternatively, if you're in state 1 and you throw the coin and you get a heads, that puts you in state 2, right? And those are the only places you can go from state 1. From state 2, there's 2 things that could happen to you. You flip a coin and you get up to 2 heads in a row, and that looks like this. That happens with probability P. Or you could flip a coin and it's tails, which puts you back into state number 1, and so that's probability Q, like this, right? And in state 3, so let me move this guy kind of out of the way. Oops. If you're in, whoa, if you're in state 3, if you have a flip the coin and you get a heads, that puts you into state 4. That happens with probability P. And if you're in state 4 and flip and get a heads, that's again probability P. It puts you into state 5 and the game's over. But the other things that could happen in states 3 and 4 is you could flip a coin, and you get a tails. And if that happens, you don't go back to state 2. You go back to having no heads in a row. And so you have these kinds of arrows like this. Let's see how I can draw this guy. It's easier on the blackboard. Although the tablet has its advantages. And so these guys both have probability Q. Right? And so that's how the directed graph looks for this 4 heads in a row. Make it a little bigger. 4 heads in a row coin toss game. Okay, now that you played around a little bit with the directed graphs, it's probably already starting to kind of percolate in your mind that there should be a lot of special properties to the collection of transition probabilities. And so that's what we're going to talk about now. This is properties of the Pij matrices. And these are the one-step transition probability matrices. And I should have said at the very start of this, or actually I should have said at the end of the last lecture, I think, we will only look at homogeneous ones. And if you remember, when we don't have a superscript of t on the transition probability matrix, what that means is we're saying that it's time independent, and those are also called homogeneous. And we are only going to work on those types of chains. All right, so this guy, first of all, you could sometimes write it just as capital P, although we've got so many P's around that can get problematic. But remember, so the elements of this matrix are Pij, like this. And if you remember the first one, the first index here, this is telling where you're going from, the state that you're going from, and this guy is the state that you're going to, right? So if it was P23, that would mean you were talking about the probability of going from state 2 to state 3. And if you want to talk about the reverse, that would be P32, right? That would be the probability of going from state 3 to state 2. Okay, so let's just list some of the important properties of this. And you might have guessed a lot of these already, or I don't know if guess is the right word. You might have realized a lot of these already, right? So first of all, let's suppose you have a state space with n states, right? So if S, how do you write this? The number of elements in the state space, if this guy is equal to n, the order of the set, right? I think that's how you say it. Then the matrix P is n by n. Right, I think that seems probably pretty straightforward. So that's one of the properties there. Another property is, I mean, this one is also a little bit silly. It's certainly the case that all of the elements, Pij, since they're all probabilities, they all have to be in between 0 and 1. They could be equal to 0, and they could be equal to 1. But they can't be bigger than 1 or smaller than 0, so they're somewhere in that range, because they're all probabilities. Now, one of the things you might have been trying to kind of piece together, or you might have realized, is that if you sum along a row, right? So that means you're holding the first index in that Pij fixed. That's telling you all the probabilities for leaving that state. So let's say it was state 2. You're looking at row 2 of the matrix. Everything in there is a probability for leaving state 2 and going somewhere else, right? So there's a restriction on what those things must add up to, right? So if you sum along a row, or I don't know how you want to say this, down a row, the words get mixed up, so let's use math. Let's just say what we mean explicitly. All right, so if we do this, a sum, if you go from j equaling 1 to n of Pij, right? So that means I is fixed and j varies, and you add up all those things. That has to add up to 1, right? So that's the honesty condition, right? All the probabilities. So in this case, like the event is left state, whatever I was, transitioned from state I, where and one of those transitions actually is going back to state I, right? So that's part of that story. So those all have to add up to 1, right? So that's one of a restriction you might have realized. Another, you might have also tried to imagine what happens if you sum down the columns, or again, since words are a little confusing, so sum along a row. Let's do this. I'm gonna copy that. I shouldn't do this. I should just write it. But anyways, so if you instead sum along a row or a column, that's what I get for that. Sum along a column, and what I mean by that is you keep j fixed, so keep the column fixed, and I guess you sum down the column is how you say that. So we change I and keep j fixed. Well, what could that be equal to? It turns out this is not as restricted, right? So let's actually here, I'll just, oops, whoa, that was kind of cool. So let's move this guy and just tell you what are its restrictions. So it's limited. It does have limits. What is the smallest value it could be, right? So this means if you keep j fixed, what's fixed is the state that you're transitioning to. And so you're looking at all the transitions that point to that state. And so if you add up all those probabilities, what can you get? Well, the lowest you can get is 0, right? That means there's no chance, there's no probability of coming back to that state. So that's the smallest value on here. It's possible. But what is the highest value? So this is a little tricky. This is adding up all the probabilities of coming back to state J. Now this, so it's sort of limited, but really, if you don't know very much about the system, it's kind of infinite. I guess what you could say is there's a better limit if you've already said what n is, right? So what would it be? I'm just thinking on the fly here. It's infinite in the sense that n could be infinite, but let's say n was fixed, right? So what could it be? At most, there's n other states that could point to J, to where you are, and it could be, there's n states pointing back to where you are, including the one that you're in, and it could be that all of them point to you with probability of 1, and so the most this could be is n. I think that's right. I'll have to think about that. I might have messed that up, but I think that's right. I'll have to fix that in post, as they say. Put a little remark on the video. But I think that's right. Certainly, though, it's limited by infinity. That's the safe limit. But it is only possible to get up to infinity if you have an infinite number of states that could be pointing back to where you were, which is possible. Okay, so now that we've seen these little rules, let's try another example. And this time we're going to actually write out, or I guess we're going to do a couple of them. We're going to write out the actual matrix and draw a picture. All right, so we didn't write the matrix before. We probably should have done that. All right, so let's look at this other example. All right, so this is an example. It's a weather model. Sorry, not that kind of weather. Weather model. Right? And so we'll name these states. So we're only going to look at whether or not it's raining or not raining. So rain or not rain. Raining. Not raining. Which I guess you could call sunny, but I feel like, I don't know, having spent some time in Scotland, that's not the opposite of rain, really. So we'll label this state 1, and state 2 is the state of not raining. Okay. And so let's say that the probability, so here's our little model. Probability that tomorrow is the same as today. Right? So let's say that is 0.8. Right? So there's 80% chance that tomorrow is exactly the same as it was today in terms of raining or not raining. That seems like a good, I don't know, seems reasonable. And so what does this mean? So the opposite of that, the probability of having a change tomorrow. So probability of a change tomorrow. That's then 20%. We're only going to have these two different rules in our model, okay? So if that's the model, well, we want to do two different things. Represent the transition probability matrix as a matrix, and then actually as a directed graph. So let's first do the matrix, because it's actually a little more straightforward. There's less kind of creativity involved, right? So what does the P matrix look like? Right, so remember these rules up here. Personally, I think it's best to work by row, because that's the one that has the honesty condition on it. So if you go along the row, you're saying, what's the probability of going from whatever state I'm in to the next one, to whatever. And so let's try that. So if I think of this first spot here, right, that's the probability of going from state 1, which is raining, to state 1. Right, so that means the probability, that's no change, right? If it's raining, that's state 1, and you go back to state 1, it didn't change. And so that's 0.8. Right? And now I'm gonna, as I say, go along a row. And so the next column is I'm in row 1, so it's raining, and I want to talk about the probability of going to state number 2, which is not raining. And so that's a change, and so that's 0.2. Right? And now we do the next line. So if I'm in row 2, So that's I equals 2. That's not reigning. What's the probability of it going to reigning? So that's a change. So that's 0.2. And then this guy is 0.8, just by the honesty condition. So I personally feel like it's easiest to go along rows because of, to work through these, because of these restrictions that you get the benefit from the honesty condition when you're filling up a row. And I guess you still get a benefit in a way when you go down a column. You know, it has to be between 0 and n or something. But I don't know, somehow I feel the honesty condition is a sort of a simpler restriction. It doesn't require any thinking. Okay, now let's try to represent this as a directed graph. So there's only two states, right? So here's state 1, and here's state 2. Reigning and not reigning, right? So if you're in state 1, what's the probability of coming back to state 1? That's no change, right? That's 0.8. And if you're in state 1, the probability of leaving it, having a change, that's 0.2. And if you're in state 2, the probability of going back to state 1 is a change, so that's 0.2. And the probability of going back to state 2, that's no change, so that's 0.8. All right, so that's our little weather model. It's a simple little two-state system. Let's try a harder one. We're going to do an infinite matrix now, so we're going to look at the Gambler's Ruin. So this is yet again the Gambler's Ruin example. And should I bring down any of the information? I think we're probably okay here. So let's just write, we've already seen the directed graph. Let's do that. Let's bring the directed graph down. That's helpful for kind of remembering what it looks like and transitioning and stuff like that. When you, how to translate for yourself between these graphs and the matrix. So I'm going to copy that and bring this down here. So Gambler's Ruin looks like this. We could have written all those words and described all the states and stuff, but this should be enough for us to make sense of it, right? So what does the matrix look like? So it's infinite, so it's not really going to be constrained on my page here. And so I'll just leave it like that, and then I'll put the brackets as I figured them out. So I go along row number 1, right? So that's in state 1. Well, look at the picture. So it says the probability of going from state 1 to state 1. So I'll put that up in the top left corner. Here, I guess I'll start the brackets like that. So that's 1, right? Well, now the rest of the row has to be zeros because of the honesty condition. And that certainly is true if you look at the picture. There's no other place you can go, right? And then that ends at 0 on the other side somewhere. Far, far away. Okay, now let's look at row number 2. So that means you're in state number 2. What are the transition probabilities? So you could go from state 2 into state 1, and that happens with probability Q. Could you go from state 2 to state 2? If you think about that, you can't, actually. There's no arrow that goes from 2 back to 2. Right? But what about going from 2 to 3? That you can do, and that has probability P. And then that's it. Q and P add up to 1, and so we've got zeros after that. Okay, now the next line on here. What's the probability of going from state 3 to state 1? Oh, sorry. Yeah. Is that right? Let me think for a second. Yeah. Probability of going from state 3 to state 1, that's 0, right? You can't. You can only go from state 3 either to state 2 or to state 4. And to go to state 2, it happens with probability Q. And you can't go to state 3. You can go to state 4, like this, and so on. And so this continues to fill up. There's a 1 in the top left, zeros all along the diagonal, and then just off the diagonal, there's a Q and a P, right? And so I'll just sort of get lazy here and just do this. Right, so it's an infinite matrix, this one, so we can't really finish it. Yeah. Well, I should say, it's not infinite, right? It ends at the largest state, which is A plus B plus 1. But that could be infinite, right? So it's infinite in that sense, that we don't actually know the size of it. Okay, now let's do the 4 heads game, right? In a row, 4 heads in a row. And we'll go back up here and steal the picture, the directed graph. You don't always have these directed graphs from which to do the matrix, but you might, and it's a good idea to kind of practice what those look like. So let's think about this guy. So first of all, there's only 5 states, so it's going to be a 5 by 5 matrix, right? So this one, we know its limits. Oops. So P looks like. So it's going to be 5 by 5. And if you're in state, so we go by rows again. In state 1, what's the probability of going back to state 1? Well, that's Q. Probability of going to state 2, that's P. Probability of going to state 3, well, that's 0. And to state 4 is 0, and also to state 5 is 0. You can't make a direct leap from state 1 to any of those. All right, now you're in state 2, our next row. Looks like I'm going to need bigger brackets here. We'll fix that later. And so what's the probability of going from state 2 back to state 1? Well, that's Q. How about from state 2 returning to state 2? Not possible. How about going to state 3? Well, that's probability P. And you can't go to 4, and you can't go to 5, right? Okay, let me tidy up my embarrassing brackets here. We'll deal with those in a minute. Now I'm in state 3. What's the probability of going to state 1? Well, that's Q. Going to state 2 from state 3, not possible. Going to state 3, so returning, nope, can't happen. Going to state 4, that you can do, and that has probability P. And going to state 5 from state 3 can't happen, right? And now row 4, I'm in row 4, I can go back to 1, and I can go to 5, and so you should see the pattern here. And if I'm in 5, I can't get back to 1 anymore, the game's over. So everything is 0, except for returning back to state 5. Right, so that's what that matrix looks like. I can finally put brackets around it. Okay, so that's how you go between the directed graph representations of things to the probability transition matrix. Okay, now we're going to talk about another kind of transition probability matrix that isn't made from moving in just one step. So, if you look at this picture over here, these different transitions you can make on the directed graph, it is possible to go from state 2 to state 4. You just can't do it in one step, right? So you have to go in 2 steps, or potentially more, right? You could go here, and then here, and then here, and then here by 2 more steps. So how many steps is that? 1, 2, 3, 4, 5. So there's a way to get there in 5 steps. And then there's a way to get there in even more, right? You keep on, you do this a whole bunch of times, and then find your way over. So there's different kinds of matrices you can build for the number of steps in your transition. We will mainly pretty much only use the 1-step transition probability matrix, but it's useful to kind of think about other ones. So I'm just going to write down over here, we're going to look a little bit at n-step. Really, you're just going to see how to define it. N-step transition probability matrix, right? And I just want to remind you before I get started with this, it's still homogeneous. We're still only dealing with homogeneous problems. So that is to say, there's no time dependence on the elements of the transition probability matrix. However, once you start talking about number of steps, there's a dependence. The matrix itself is dependent on how many steps you talk about. So in that way, time kind of enters into the definition or into the thing we want to talk about. But it's not like for the number of steps, we get some different answer at time today versus time 3 days from now. It's still the same transition probability matrix for however many steps you're allowed. Okay, so let's just write down the reason. The reason I'm kind of harping on this, I think, is because the notation is a little bit ugly. So we're going to define the n-step transition probability matrix to be the following thing. So first of all, it's P again, capital P, and then we'll put as a superscript n, right? Now, we never had a superscript on capital P before, but we did have one on little t, and that was the thing that determined whether or not it was homogeneous. So that's why this notation is pretty ugly. So it might be better to not have that as a superscript, but just have it as like a regular P parentheses n kind of thing. But we'll leave it like this, just because that's how it is in the notes. But I don't think we really use this that much, so it's okay. Anyways, and so this guy is going to have elements, and the notation is changed for the little guys, Pij, and then we put not a superscript, but parentheses n. So it's like we invented this notation and then realized how to fix it. I probably should just fix it, but anyways, I can't. I'm too afraid to change from tradition. Man, I'm becoming British already. Okay, so let's look at this guy. So what are these elements? What do they look like? So Pij for the n-step transition probability matrix. What are these things? What's the definition of them? Okay, so they're the probability of going from state. Oh, how do we say this? From state. Oh, I gotta go back and look, right? Man, so the first element is the row. That's where you're going. Oh man, I went all the way back. Did I not write it in here? There it is. That was a long walk. So the first index is where you're going from, and the second index is where you're going to. So from is I, right? And so let's go back now and see where we are. Okay, and so what this looks like is the following. So we're saying we're going to a particular state X, and then we'll put underneath it n plus, sorry, hang on. Oops, I've already messed it up. M plus n. So it's n steps away in time, or steps, from where you were at time m, right? So that's where you're going to, right? And the next one is where you're coming from, right? So that means at n steps earlier, it was at time m, and this is I, right? So that's going from I to j. Geez, did I mess it up again? I think I got it right. Let's take a look. One more wander up here. From I to j. Yes, got it right. Yeah. Okay, so that's what this guy looks like. And then there's just one more thing to point out. Since everything is homogeneous, there's a further thing you can do. So since it's homogeneous, what does that mean here? It means that there's no dependence on m, right? It doesn't matter what time it was you started. It only matters that you're going n time steps away. So let's just duplicate this. And there's one way to see this, actually. It's pretty obvious. If you get in the habit of using indices a lot and just algebra a lot, I guess, there's no m on the left side of the equation. So there better be a good reason for it. And the reason is it doesn't need to be here either. So we just get rid of it. So you could say 0 and to state n. Oh, I guess you can't say, yeah, that's it. Although what were we saying? We start at state 1, so you can't have 0, right? Oh, so I've messed it up. So I gotta do, oh man. If you can only start at 1, you gotta do it like this. I gotta put n plus 1 over there. Got all these things to move around. Okay, so this guy becomes 1. And this guy becomes n plus 1. Like that. So it's n steps away from the state that you started with. Or you could put anything else in there. You could have them starting at state 4. So x1, instead of x1, you could have x4. You can just do it like that. That's the same. You could put anything you want there for the m. In other words, the m doesn't matter. Yeah. So yeah, that's how the n-step transition probability matrix notation looks. Now, before I transition on to the next kind of important topic, I want to just make a note. All right, this is something I probably should have put. It fits okay here, I guess, but it's not necessarily the best place to put this. But it's got to be in here. I should have put it in here yesterday, I think, or in the last lecture. There's something that you can kind of get a little carried away with the memoryless property and kind of overuse it and get yourself into trouble. I think I've probably done it a few times in my speaking, but the idea is the state xn, this memoryless thing is saying something like, we only need state xn minus 1 to predict stuff, something like that. It's not quite right. You can overstate this. No pun intended. Ha ha. What we really are saying is that, so let me just write this out. State xn, it isn't only dependent on state n minus 1. Or these aren't states, but like chain element n isn't only dependent on state or on chain, or let's not even use a word. Always best to avoid words. N plus 1, right? Or minus 1. It's not the only thing that influences xn. It's just the thing that best influences it, or has the strongest, or is all you need, sort of. I don't know if that makes it sound right. I think that's overstating it, right? So let's say this way. But it is best dependent, or fully dependent. Fully might be too much. It is best dependent on xn minus 1. So let's try to, so you see how getting ourselves into trouble with words here, but like, imagine the drunken walk problem of the guy going home from the pub, right? It's not the case. So let's say you think of him at his 4th step, right, along the process. It certainly is the case that where he is in his 4th step, between the wall and as he's moving along, like where is he between the wall and the river? It certainly depends on where he was in his very starting point, right? If he started right along the river, he's not very likely to, on his 4th step, be up by the wall, right? So there's definitely, it might even be impossible depending on how far away the wall is. So there certainly is a dependence, but it's still the case that if you want to say something about what's the probability of getting to the next spot, the only thing you need, you have as much as you can possibly get, as much information as you can possibly get by just knowing where he just was. So if you want to know where he's going to go next, the best piece of information that'll help you most is where he currently is. You could get some information by knowing where he used to be, but it's best, or you get the most, if you know where he is currently. You're not going to get any more information if you know where he is currently by adding things you knew about where he was before that. That's probably the best way to say it. But so be careful with this memoryless property. Try not to sort of overuse it. Okay, now we're going to finish today's lecture with a pretty important set of equations. And so we're going to make a proposition, that is the equations, and then we'll prove the proposition. So this goes by the name of the Chapman-Kolmogorov equations. You may have heard of this before, maybe even in a different module. So we'll write this as a proposition. So proposition, oh well, hang on. I better just make a section out of it. So this is the Chapman-Kolmogorov. I probably have mispronounced that name. Equations. I think this might also go by different names. People might call it something else. I was talking to one of the other lecturers here, and he saw that, and he said, I call this the such-and-so equation. But so you'll encounter this in different with different names. And so we'll write this as a proposition. So proposition, and this is the Chapman-Kolmogorov proposition. Or I don't know, you could call it theorem or whatever. I'm not going to bother. But it's the thing that gets this name. And in the notes, you'll see it written in two ways, like as if there's two different propositions, but they're pretty obviously the same thing. So the first one is to write the following thing. So we say that the transition probability matrix in m plus n steps, that's what we want to look at. So it's a multi-step transition probability matrix. So we want to look at the elements of this matrix, and it's making making m plus n steps, right? So that's the elements of that matrix are what we want to look at. And the claim is that these are written in the following way. It's a sum over k, where k is an element of the state space. And then we have these two different things here. So p I k of the n step transition probability matrix times p kj of the m step transition probability matrix. All right, and the second version of this isn't really different at all, but I'm just going to write it that way because it's how you see it in the notes. It just says that p m plus n. So now this equation is referring to the entire matrix, right? As opposed to just the individual elements. So it says that p m plus n, so that's the m plus n transition probability matrix. And then what's on the right-hand side, you probably have already guessed, if you just look at this for a while, and depending on how much you've been doing linear algebra lately or anything, this is just matrix multiplication on the right-hand side. And so if you haven't been doing that and writing out matrix multiplication as a sum, maybe in the last year, you might not have recognized that straight away. But that's what that is. And so we can just write this as a matrix product. So it's the product of matrix Pn, so the n-step matrix, times the m-step matrix, right? And then there's a little corollary that goes along with this. So this is the proposition, and this is the corollary. For homogeneous chains, which are the only ones we're going to look at, I think. The following is true. If you look at the n-step transition probability matrix, so this is where that notation kind of comes from, this is actually just equal to the one-step transition probability matrix to the n power. In other words, p times p times p, and there's n of these. If just to remind, because there's so many superscripts of n going on here, this is just to remind you what that means, right? So that's a bit of a corollary that comes from this proposition here. All right, so we're going to go ahead and prove this guy now. It should be pretty straightforward. All right, proof. Okay, so the first thing we're going to do is write out the left-hand side in a sort of a funny way. So we'll say often the beginning point for a proof. Pij, so the m plus n matrix, m plus n transition probability matrix. So we're going to write this in the following way. So we say that's a sum of, oh, sorry, I got ahead of myself. Oops, getting ahead of myself. We're going to say this is the probability, right, this is an element of that matrix, of being in state x, or being in state j at moment x plus m plus n, right? So you went in m plus n steps, you went, how does this go? From I to j, right? So this is where you are, and where you came from is, I'm just going to put at x0, so at time 0, you were at some place. I don't know what it is, right? But m plus n steps later, you're at state j, right? So this is the m plus n transition probability matrix, so that's fine. And then the first thing we're going to do is sort of expand this a bit using the total conditional probability theorem, right? So we're going to say this is equal to the probability. So what we're going to do is we're going to insert state k happening at time n, and then we're going to sum over all the possible different state k's, right? So we're going to say sum over k of the probability of being in state x m, or having chain x m plus n being in state j, given, now here's where I insert the state, that at chain n, moment n, we were in state k, and that initially you were in state I, right? And so this is we're conditioning on this, and so we can now multiply this by the probability of being in state k at time n. So I'm splitting off the n here, given that at time 0 you were in state I, right? So that was done by the total conditional probability theorem. The next step is to use the Markov property, right? So this is a Markov chain, these x's, and we are going to use I think it's the alternate definition, the one that I wrote out. And so we're going to use the Markov property to eliminate this guy, right? Oh, I didn't even finish writing it properly, geez. So remember, it certainly is the case that the probability of being here depends on the fact that you were here, but you don't get any more information about the chance of being here if you know a closer point in time where you were. So we can throw this guy out, right? So that's the idea. So I'm going to actually just duplicate this line because it's a long one. And so that's done by the Markov property. And so in the spirit of what we've been doing with Markov property enforcement, I'm just going to remove this guy and move everything to the left. Right? So that's the sort of memoryless property. It's the alternate definition that we saw. And now I'm going to make use of the fact that I'm only interested in homogeneous chains, which is the case. Right? So if we're only interested in homogeneous chains, we saw this before. We can write the following. So this is equal to, well, let's just duplicate it again. We'll see what we're going to change. So what we're going to change here is that we want it's the first probability that we want to edit. All right. So we're going to say we didn't start from state n. let's suppose we start, let's say 0. And here, so that means I take away this n, right? So I'm m states away. Oh, sorry. Yeah. So the first line up here, so I got a little tangled up. So this line up here is saying I'm m time steps away from time step n, and here I'm m states away from time step 0. Those are the same because of the homogeneous property. Right? That look good? Now, if you stare at this long enough, you should see what I mean, I just said it, or just read it over and over again. But so this is clearly here to here in m steps. That's the m step probability transition. M step transition probability, right? So I'm going to write this. So sum over k. So this is p. So it's in m steps. So it's the m goes in here. And you go from, so let's see. So how do you read this? The probability of being here. So that's where you go to, given that you were here. So you go from k to j. So we put this k, j. Okay, good. And then this guy, we write the next term is probably, this is an n-step probability matrix, right? And here you're going from I to j. Oops, did I get that right? From I to k. No, there's no j here. Yeah. And this is the thing we were after, just rearranged, right? So just with the terms in the opposite order. Here, I'll just to prove it. Let's copy this, paste it, and we'll move the things around. Whoop. These are the benefits of using the tablet. You can't do things like this on the blackboard. Although maybe that's annoying if you're taking notes with paper or something. So sorry about that. I'll try to. I should get out of the habit of doing this, but I can't help it. You got to make use of the nice things. Yeah, and that's the proof of the Chapman-Kolmogorov equations.